And what happens in these models is they just say these boats are emitting a certain number of particles and into this grid box, and everything just gets instantly diluted. And the problem with that is that we miss a large amount of small-scale microphysics. So that's really what I'm looking at with my project. What's small-scale microphysics? In particular, particle coagulation. So coagulation is when particles collide together and stick. So you take two small particles, they stick together, they make a slightly larger particle. But now you have fewer particles to make your cloud thicker, so it won't be as thick. And the most important thing to note is that the coagulation rate is proportional to the concentration squared. So you have two particles in a box, they can each collide with one another. If you double the number of particles in that box, not only can does each particle have twice as many other particles to collide with, but there are now twice as many particles to collide with each other. So with these proposed ships, there are going to be very, very large particle concentrations in there, and we're probably going to see large amounts of particle coagulation. So I built a model, the multi-shell plume model. So we emit particles from the ships into this multi-shell model. Right now I'm using 10 shells. We track the particles through 100 size bins between 10 nanometers and 10 micrometers. We calculate binary coagulation. We have turbulent diffusion between shells. And here I have that we see larger particles in the middle because our concentrations are going to be larger in the middle. So we're going to see more coagulation there. So we're going to have larger particles. So they're going to diffuse out, and small particles are going to diffuse back in. So here we've just run kind of a base case. So trying to get as close as we can to the specifications in the Salter paper. And as we can see, this is kind of what we'd expect from coagulation. The distribution is moving a little to the right and shrinking a fair amount. So here I have everything detailed over time for each of my shells. Fraction of particles remaining on the y-axis here. It's going to be a theme for the rest of my results because we really want to know how many of the particles we're emitting are making it to the clouds. So we have the average here in the black dotted line. And we can see that under the conditions we expect, we see almost a 50% loss in particles. So what we've done is played with a bunch of the different parameters and seen how they've affected the number of particles we get back out. Notice the units over here. So when we vary the mean diameter of the particles we're emitting, we actually don't see a huge change from 61 to 69%. And this is because there isn't a huge difference between the chance of coagulation between smaller particles and larger particles. We see much bigger effects when we vary some other parameters. So here we have a graph of varying emissions rate. So here we have our base case, and then here we cranked up the number of particles to be emitted by a factor of 10, and here we turn it down by a factor of 10. So when we turn it down by a factor of 10, many more of our original particles survive. So we cranked it down, we cranked our emissions down by a factor of 10, but we only, we end up with a factor of 5 less, a factor of 5 fewer particles left when we finish. We crank it up by a factor of 10, we lose a lot of particles. So cranking it up, emitting 10 times as many particles only gives us about 3 times as many particles when we're done. We've also tested the dependence on wind speed, the radius of the stacks that these particles are being emitted from, and the stability of the boundary layer. I don't really have time to go over those today. But if you'd like to see them, I can obviously show them to you later. So what we're planning to do with this going forward is to find a good way to parameterize global models so that they can take these factors into account without having to do huge computations. that's going to be my work going forward. So in conclusion, we've looked at sea spray geoengineering and how it can affect global warming. We've found that geoengineering is probably not going to be as effective as it's currently stated to be with this method. And we found that the initial concentration plays the very largest role in how many particles we're going to lose due to coagulation. The rate of expansion of the plume is secondary, but still has a very large effect. I'd like to thank Robin Stevens and Jeff Pierce for their help, and also wish Chris Wainwright for his help in my lab. Thank you.
Any questions from the audience?
Yep.
So you're talking about these clouds that would reflect the sunlight back in space.
Yeah.
How do you know that this reflected light won't just be absorbed in the atmosphere by, like, let's say, water particles or something?
Wait. The direct aerosol effect, which is the absorbing of sunlight by individual particles, actually plays a very small role in the absorption in the atmosphere. So yes, some of it will be absorbed, but it's a very small fraction of the light that's reflected back into space. Yeah.
This question might be somewhat outside the range of your talk, so just let me know. But this stuff is going to be mostly happening here in the equator.
Yes.
Right. So this isn't going to help change at all the solar energy coming in near to the poles.
No.
Right now we're experiencing a lot of climate warming due to these huge feedback effects.
Yep.
So I guess my question is one: how efficient does this make this method overall? Then, if we can't apply it to the poles, and two, if we change the global temperature gradient between the equator and the poles, won't that have a large impact on overall global circulation? So it'll be
Yes, absolutely. Well, I'll address the second part of your question first, and that's the largest reason why there are so many global studies being done about this. And one very good result that came out of a study recently was that we can use this method to either get temperatures back to pre-industrial times. We can get sea salt or sea ice coverage back to pre-industrial times, or keep rainfall the same. But we can't do all three at once. So there are very competing factors in doing this, and that's why there are so many studies going on.